Okay, hi, and welcome to the third lecture of Biomaterials 1. This one is the first introduction in a two-lecture part about polymers. So Drexel Chemistry Department actually has a whole three-course series on polymers, so you can get into a lot of details of polymer chemistry. I'm going to try to condense it to two lectures, where today we're going to talk about the basics of polymers, including, let's get into it. So today we're going to talk about what makes polymers unique compared to other biomaterials. So that's generally their very directly related structure-function relationships. And then we'll talk about what makes polymers unique in terms of their mechanical and thermal properties. And then in the next lecture, we're going to talk about naturally derived polymers and also hydrodols and maybe some more special topics of polymers. Okay, so first of all, medical polymers is a huge market, $1.2 billion and growing, most of that in North America. The vast majority of the polymers that are classified as medical polymers are like PVC, polypropylene, polystyrene, and these are they're mostly found in biomaterials that are external to the body, but they're still considered medical devices by the FDA. So that would be surgical equipment, syringes, gloves, blood bags, anything that is related to medicine but is not implanted is actually the vast majority of the medical polymers. I want to focus today on implanted polymers. Actually, I guess I'm not focusing on that because today I'm just giving intro to polymers. But for some of, I guess I'll point out if I'm talking about if they're going to be implanted or not. So who are the major manufacturers of medical polymers? It's your same medical device companies that do a whole lot of things. A lot of the smaller ones are owned by the big guys like Johnson & Johnson and Synthase. Gore, which was the maker of Gore-Tex materials that a lot of your jackets and school bags are made of. A lot of people don't realize that they have a huge medical polymers arm. So these are some places you might want to apply to if you're really interested in polymer synthesis. Okay, so polymeric implants that are used, that are actually implanted in the body and really interact with the body. A really common, probably the most popular use of implanted polymers is in total joint replacements. So they can be just a spacer in between two articulating metal or ceramic prostheses, or you can have an entire arm of the prostheses made of ultra-high molecular weight polyethylene. There's also a really big stent market with polymers that are biodegradable and not. And of course sutures, which have been around for thousands of years and they've always been polymers, but now we're getting really fancy with the design of these sutures and so that they're biodegradable and you don't have to remove them anymore. So some common biomedical polymers, ultra-high molecular weight polyethylene, as I just said, silicone, PLA, polylactic acid, and polyglycolic acid are your most common biodegradable polymers, and they're sort of like the go-to biodegradable polymer when you're just starting out with that as a design constraint. Nylon has been a suture for a couple decades now, so you can see that they have really diverse applications. So as far as advantages of polymers, the biggest advantage is that you can easily tune their properties just based on their structure. And so you can just change processing parameters or just buy different polymers and completely change what happens to the resulting biomaterial based on that. And so polymers and their properties cover a whole wide range of applications because of that. And you can also modify the surface properties if you need to do that too. The biggest disadvantage is probably that they're difficult to sterilize, which of course is a really big problem for biomaterials that are going to be implanted. They have to be very sterile. And then they also easily absorb water and also other biomolecules from the surrounding environment, which could cause and does cause deterioration of the polymer when you implant it. And even shelf life is actually a difficult part of polymers. You need to make sure they're not just spontaneously deteriorating, just sitting on the shelf. So these are important things to consider. And then they also experience the same mechanical wear and breakdown that any other biomaterial would. And also, if they're biodegradable, whether or not they're biodegradable, they might leach some toxic compounds into the body as they deteriorate. So especially ones that are designed to be biodegradable, you have to make sure that the byproducts are not going to cause an adverse reaction in the body. Okay, so let's get into the basics of polymer chemistry, because the structure of polymers is really what determines their function. So you have to understand their structures in order to be able to design a polymer for particular use. So this is probably the simplest polymer that you will come across. It's polyethylene. There's a bunch of different ways to draw a polymer, so that's why I put them all up here so that you can see that they all mean exactly the same thing. Polyethylene is polymerized from ethylene, which is the starting monomer, and then it's polymerized into a long chain that's just a carbon backbone with hydrogen molecules on either side. And you can have it, that N outside of the parentheses is how many repeating units you have. So here the repeating units is 2 carbon atoms with hydrogens bonded to them. So most polymers are organic and based on having a carbon backbone, but they can also have other things in there, like a lot of times you'll see oxygen molecules or silicon molecules that change the properties, and we'll discuss that more in a little bit. You can also have polymers that are based entirely on silicone or on phosphorus, and those are called polysiloxane and polyphosphazines, respectively. But if you're wondering, polymer, the name is derived from poly, meaning many, and mer is the single unit. Mer means, I think, unit or something. I think it's Greek. But anyway. Okay, so basics of the 3D structure. Polymers can be either fully amorphous, or they can have some crystalline domains, but they can never be 100% crystalline because polymers are so long you couldn't possibly get them all to order in the right amount. So you either have amorphous or semi-crystalline. In a semi-crystalline, you can see, okay, I'd just like to apologize already for some of the images in this lecture are going to be a little dark. My scanner was broken, so bear with me. But basically, polymers will have some crystalline domains and some amorphous domains, and that actually really determines their properties as well. So it's important to understand that they can have these different phases. So types of polymers. The most common are, you'll have a linear polymer, so we just saw polyethylene, which is just completely a string of repeating units. It can also be branched, and those branches can also cross-link with one another permanently, covalently, and then that forms a network, a cross-link network. And cross-link networks are often called elastomers, and these are permanent covalent cross-links so that these polymers will not be able to be reprocessed back to their single chain form. But they're cool because they can, the long chains ensure that they have a viscoelastic response to stress, but then the fact that they have those covalent cross-links means they are going to they have an elastic response and they come back to their original shape. So we're going to talk more about viscoelasticity later. I'm getting ahead of myself a little bit. Okay. So you can have a homopolymer, which is, we saw polyethylene, that's a homopolymer, that's just the same repeating unit over and over again. Or you can have a copolymer, where you have different repeating units mixed in with the other ones. So they can be, so in this diagram, A is one repeating unit, so it might have been those 2 C's with the 4 H's around it. And then B is another repeating unit, so maybe it's an ester molecule. And depending on the synthesis, they can be just randomly distributed, or they can be controlled so that it's every other one. That's an alternating copolymer. They can be a block copolymer so that you have literally blocks of the different repeating units, or they can be grafted, and that's the easiest way to form a cross-link structure. So, and also any of these repeating units, they don't have to be just like a linear mer. They can have pendant chains and functional groups coming off of them, which is another really easy way to control their properties. So let's take a step back and talk about how you make a polymer, because I think that's helpful to know, since you can, by controlling the actual structure, even within the backbone, that's how you can control a lot of the properties for the resulting application. So there's three different ways to make a polymer. The first is a chain reaction, also called addition polymerization. The next is condensation polymerization, and then there's ring opening polymerization. So let's just go through these briefly without getting into too much of the details. In chain polymerization, you have the monomers and you have some sort of initiator that when you add some energy like heat or UV light, that breaks into a free radical that's extremely reactive. And that attacks that vinyl group, the double bond on the carbon, and makes that a radical. So now now the free radical turned the monomer into its own radical. And then that radical can go and attack double bonds on another monomer, and the chain can just keep repeating until eventually it collides with another radical, and that forms its own bond, and it's over. That's called termination. So that's why you have initiation, propagation, and termination. In some cases, you can actually remove the ability of the polymer to terminate, and that's called a living polymerization, so that it would just, if you gave it enough substrate to add onto the chain, it would just keep adding onto the chain. And that's actually how you make block copolymers, because you can have all the A's in there, and the A's make really long strings until they're all used up. And then you put in the B repeating units, and then the B's add on. And then you can add in more A's, and so then you can keep controlling the molecular weight of each block. Okay, so that's chain polymerization. Condensation polymerization is also a really popular way to do it. Two molecules are combined in a reaction where that loses a molecule, usually water or hydrochloric gas or some other small molecule. An example of this is nylon 6,6. And the reason why it's called condensation is because the resulting polymer has less mass than the sum of the two that made it, so it was condensed into a smaller form. And then finally, ring opening polymerization is pretty straightforward in how that works. The ring opens up, and then they polymerize together, and that's how you make a lot of things like polycaprolactone, and also PLA, PGA, PLGA, the common biodegradable esters that I talked about earlier. Okay, so all of that should make you think about the fact that you can control the molecular weight, or at least the molecular weight is going to be an important thing that comes out of the synthesis, that you need to know what the molecular weight is. So there's two ways to talk about molecular weight. And it's based on the fact that when you have a synthesis of a polymer, it's not going to be it's not going to have one size of the chain. It's going to have all of the chains in this batch that you make are going to have a distribution of sizes. Some are going to be small and some are going to be large, and it's actually usually distributed around a bell curve. And so when somebody asks you what's the molecular weight of that polymer you just made, you can talk about it in a number average molecular weight or a weight average molecular weight. So the number average is pretty straightforward. You basically just take the total mass of the whole sample and you divide it by the number of molecules, and that's your number average molecular weight. So the way you could do that, so it's notated with the sum of n times n being the actual number of molecules that have the mass m. And so if you take all of their sum and you divide it by the total number, that's how you get number average molecular weight. So that's kind of straightforward, but I think that weight average molecular weight is more confusing, or at least not in theory, but actually calculating it might be a little bit harder. So you should think of it as a weighted average. It's actually weight average because it's determined by the weight percent of each fraction, but I like to think of it as a weighted average that's weighted based on the mass of those molecules. So that's because larger molecules account for more of the total mass than the smaller ones. So if I tell you the molecular weight of something is 50,000, but most of the chains are actually 75,000, and then there's just a couple that are 2,000, well, that's something that would be good to know about. Well, most of them are actually 75,000. Okay, so that's why the number average and the weight average are going to be different. And if you take their ratio, that's called the polydispersity index, and it basically tells you how tight or broad that molecular weight distribution is. But because I think this is important and confusing, I have an example with how to calculate molecular weight. So if you make a polymer and then you weigh it and it weighs 10 million grams, and you know that it's made up of 100 polymer molecules, which you can determine using gel permeation chromatography, then you can calculate the number average molecular weight by just doing 10 million divided by 100, the average molecular weight is 100,000 grams per mole. So that's the number average. However, GPC tells you that 70 weight percent of the molecules are actually 150,000 grams per mole. 20 weight percent of the molecules are actually 50,000 grams per mole, and only 10 weight percent are 25,000 grams per mole. Then you can actually weight the amounts of each of those based on their weight fraction in the total amount to get a molecular weight that's based on the weight distribution. And so the calculations are right there, and you get a molecular weight by weight of 117,500 grams per mole. So how do you do the polydispersity index? You just take the ratio, and it's 1.1175. So it's a reasonably monodispersed polymer, you could say. Okay, so that is how you make a polymer, and that's the basics of how we talk about a polymer. Okay, despite the fact that there is a picture of spaghetti on this slide, this is actually the most important slide in the entire lecture. And it is discussing what makes polymers so special, why are they different than their small molecule counterparts that you made them from. So there's three things that are that you should think about when you're thinking about how a polymer will respond to application of stress, a change in temperature, or anything that you're going to do to it. It's all based on these three principles. Okay, so the first is chain entanglement. If you have small molecules and you put them together, they are not going to entangle, so they can easily disperse, and that's not going to have any response to a force, right? But if they're entangled and you try to pull it apart, it's going to be harder to pull them apart, and so that you have some response to a force just right there, just in the fact that they're entangled. Also, because they're entangled, you have a summation of the interchain forces. So if there's any polarity on the side group, so if there's any like ionic bonding between pendant side groups, that's going to be multiplied by 100,000, depending on the molecular weight of your polymer, because they're all going to react with each other. So those two even compound each other, the fact that you have entanglement and you have interchain forces acting. And then the third one is time scale of motion, which basically means that interactions take time, and in a small molecule, it's a negligible amount of time. If there's transient, van der Waals forces in between molecules, that's negligible time for a small molecule. But when you multiply that by 1,000,000, that's a lot. So when you're pulling on a polymer, the bonds about all of the different around the backbone have to actually rotate in order to accommodate a change that you're applying to it. So that takes time, and that's why we have time-dependent responses to mechanical forces that are applied. So these three things, whenever someone asks you a question, like someone asks you to guess what might happen when you increase the molecular weight of a polymer, like will it be harder to pull it apart? The answer is yes, because the chains get entangled, the forces are interacting with each other more, and they're summing, and because everything takes a little bit of time, so it's going to be a time-dependent response as well. So you should always think about these three things when you're trying to predict a response of a polymer. So now we're going to go into a lot more detail of how those three things play out in terms of mechanical properties and thermal properties. So influence of molecular weight on properties, what we just said. If you increase the chain of a polymer, that increases entanglement, and increases any forces that you're going to have, and increases the time scale of motion. So you'll see an increased melting temperature. So once you actually go and do the tests on your polymer, this is what you're going to see. You'll have increased melting temperature because the chains now can't move as much as they could before. And in order to make something melt, you need to have free moving chains. That's what a melt is. So if they can't move as much, that's a higher melting temperature. Increased interchange forces means that the material can respond or can withstand greater forces without deforming so much, and that's a higher modulus. That's the definition. So that's what that does. And it increases the viscosity of the polymer sample because everything takes a little bit longer, because that's the increased time scale of motion. So because you have a distribution of molecular weight and not just this is the molecular weight, sometimes there's short chains in a polymer sample that can actually interfere in the packing of the molecules. I guess what I should have pointed out in this diagram, also known as a picture of spaghetti, in that this is generally an amorphous polymer, but I guess if you see some aligned sections of spaghetti, like right here, this is a crystalline region. and this is a crystalline region. This is a crystalline region. So this is a semi-crystalline spaghetti polymer. So the fact that, so actually what I didn't point out is that increasing the molecular weight is also going to decrease crystallinity because it's harder to pack them. Okay, so if you have short chains in the polymer sample, just because that's how the synthesis happened, and maybe you didn't control it enough, and so there's some really short chains, that is going to interfere in the molecular packing, reduce crystallinity, and that'll lower the melting temperature and lower rigidity and other mechanical properties. And you can also intentionally add in small molecules in order to intentionally reduce those things, and they're all called plasticizers, whether you put them in there on purpose or not. So that's one way that you can control the properties. Okay, so another really obvious way of controlling the structure or controlling the properties of polymers is by changing their actual molecular structure and changing the molecules that are going into making it. So the picture on the left shows that if you take a carbon backbone and you make it more flexible by taking out some of the carbons in the backbone and making it an oxygen so that the bonds are freer to rotate, then that makes it more flexible. Or the same thing if you add a silicon atom instead of oxygen, makes it more flexible, and so that will decrease the melting temperature and mechanical properties because they're more mobile. So they won't be able to withstand a force like their more rigid counterparts. So it's all going back to those three principles of chain entanglement, interchain forces, and timescale of motion. Same thing if you make the backbone more rigid by adding in a benzene group here, so they can't rotate, they really can't rotate very well. That's going to increase the melting temperature and the mechanical properties. I just wanted to compile some side groups here because I think a lot of times it's easy to hear, oh, I added a benzene group or I added a carbonyl group, and you don't actually know what that looks like. But it's helpful to know what they are because it really does change the properties really easily. So this is just compiling it for you so that you can study it and try to understand what they are. And these can also, you can also see them within a group too, and they have slightly different names. Okay, so you can see how the side group being a completely different atom or something would change the properties of the polymer. But what if you have the same actual elements, they're just larger? What does that do? So now we're talking about the side chain. So you have a long polymer molecule and the side chain is coming off it. If it's just so this is actually for polyethylene, this is real data. So if you have just a hydrogen atom, the melting temperature is 140 degrees. But if you increase the size of that side chain, it interferes in the packing of the molecules. So it decreases crystallinity, which in turn decreases the melting temperature because it's not so difficult to add enough energy to make them all mobile. So that's why the melting temperature goes down. Until you get to a certain point where that side chain is so large and so bulky that it itself hinders interchain movement. And then you see an increase in melting temperature again. So that's what we see here with these bulky side groups that go from to 196 and 350. So that's how the size of the side chains can affect things too. And that just goes back to entanglement once again. Okay, so an example of how molecular weight has been used to design a better biomaterial. Ultra-high molecular weight polyethylene has I think it's the highest molecular weight polymer that exists. And the strength is actually derived from van der Waals forces, which are usually really, really weak between molecules, but because it's multiplied by 2 to 6 million, it actually results in a really strong polymer. You also have really linear chains in polyethylene, so they have very high crystalline structures, which enhances the mechanical properties. And then recently, maybe in the last 30 years, researchers and manufacturers started really highly cross-linking the polyethylene even further to make using gamma radiation, and that actually increases the resistance to wear for a total knee replacement or a total joint replacement prosthesis. So that is an example of how you can increase the molecular weight and you can have cross-linking in order to change the mechanical properties. I should point out that cross-linking doesn't always increase the mechanical properties of polymers. because sometimes when you enforce artificial cross-linking, that actually disrupts the natural order of a polymer, and then you have a decrease in, I guess, in overall crystallinity, which actually decreases the mechanical properties. So it really does have to be considered on a sample-to-sample basis. Okay, but they cross-linked it in order to reduce the wear, but that doesn't mean that it's done yet, the research on polyethylene, because you still have a lot of wear and a joint prosthesis just from the articulating surfaces. And so a really active area of research right now is, why do bones degrade when you have a knee implant, and it seems like the bone ingrowth is really good into the femoral prosthesis, but somehow 15 years later it starts dying? How could it have worked so well for 15 years and then it stops working? Well, what they recently found is that the polyethylene that's either the spacer or actually a part of the prosthesis starts to wear away and generates submicron particles of polyethylene. These are very small, and then they go into the bloodstream, they diffuse around, and they cause an adverse inflammatory response by the macrophages that are present in the bone surrounding the implant, and the macrophages actually start to attack your own bone and degrade it, and that's when you have osteolysis. So this picture is actually showing how the bone started to degrade. You can see that it's less dense there in the x-ray, so it started to degrade around the prosthesis, even though this is the metal, not the polyethylene. So the polyethylene wear actually affected the biomaterials in a slightly different, it's the same, it's the joint, but it's in a different area that it happened. So that's still a really active area of research, is how to decrease the wear of ultra-high molecular weight polyethylene. Okay, so we sort of started talking about mechanical properties. All materials are not perfectly elastic. Even if you have, a metal or something, they may seem perfectly elastic, but actually they're viscoelastic. And so, an ideally elastic behavior would mean that they, you stretch or compress, and all the energy is stored in the chemical bonds, and then it returns to its original form. And then an ideally viscous behavior is if you apply a shear stress like flow over something, the material will flow, and then all that energy is dissipated in the flow. So it's different ways of storing and dissipating energy, but nothing is ideally viscous or ideally elastic. Everything is somewhere in between. And for polymers, they're like smack in between. They're viscoelastic. So this actually changes a lot of their response to forces, and so that's what we're going to talk about now. So viscoelasticity, the basic definition is that mechanical properties are time-dependent and rate-dependent. So the bonds, so we talked about this, when you have polymers that are wrapped up together, as soon as if you pull on them, first of all, the bonds have to rotate, which takes time. You multiply that by how many times it happened. And they're also interacting with other chains around them, which is also going to increase the time. And so that is the time scale of motion. That's why mechanical properties are time-dependent. And they're also rate dependent, so we can look at this empirically. This is a study of brain matter, of gray and white matter. And so they did, I believe this was compression. It could have been tension. But basically the dots correspond, the open dots and the colored ones correspond to the same sample. So if we look at, let's see if my mouse works here. If we look at this square, is 0.01 strain, so 1% strain per second. When they increased it to 10% strain per second, the mechanical properties increased. So the faster, and that's actually true for all of these. So if you increase the strain rate, they actually can withstand a higher force. So that's why the strain rate is really important when you're studying a viscoelastic polymer. And it's also a really interesting reason, or a really important point, that if you're going to test a material that you're trying to make biomimetic, and then you look in the literature to try to compare it to gray matter, say, if it's not the same strain rate, you absolutely cannot compare it, because these are viscoelastic and rate-dependent materials. So and actually you should always just completely, since everything can really change the properties that you get out of a mechanical testing, you have to completely replicate everything in order to be able to compare it. Okay, so this was just a simple compression or tension, I can't remember, but what happens if you do tests that are specifically designed to measure the viscoelastic properties of materials? So there's two basic ones, creep and stress relaxation. So creep is the slow progressive deformation of material when you hold it at a constant stress. So the picture here depicts if you just put a 5-pound weight on a viscoelastic material, first it would have a certain deformation, and then over time, even though you're not adding any more weight, it actually has more and more deformation, even though you didn't change the weight at all. So that's constant stress, but time-dependent increase in deformation. Stress relaxation is the same concept, but you're holding it at a constant deformation. So let's say you pull something that's viscoelastic down and you say, I'm going to hold it here. The stress that is applied in response to you holding that decays over time. So it actually gets easier and easier to hold that down over time because it's time-dependent properties. So in more detail, for creep, a purely elastic response, if you had a graph of strain over time, so in the upper left-hand corner, if you apply an instantaneous strain, or an instantaneous stress that you hold constant, the strain is going to stay at that spot because they are linearly related through Hooke's law. So and the modulus dictates what stress is going, or what strain is going to happen from a given stress. A purely viscous response is you have permanent deformation because it flowed away. So it's not going to return back because it has no elastic component. In a viscoelastic material, it's related strain over time. So if you apply a stress right here, you have more and more deformation. So strain is increasing with time until you remove the stress, and then you have a recovery stage. And so you can describe that mathematically, just a simple mathematical function. You just fit a curve to that data, and it's based on the initial strain and also a time constant. And that characteristic time constant you can use to describe how much a material creeps compared to other ones. And so creep is actually a measure of, can be a measure of fluid flow if it's a swollen network, but we're going to talk about that more in the hydrogel lecture next. And also you can relate compliance is directly related to the time-dependent strain. So it's sort of like Hooke's law, but it's based on time. It's not just based on stress and strain. So for stress relaxation, you apply a constant strain, and then the stress required to keep that strain decreases over time. And so just fit a curve to that, an inverse exponential curve that's based on the initial stress and also another time constant. You can define a relaxation modulus as being directly related to the rate of strain rate change. But there's some models to help you understand a little bit better where this math came in, or just to describe it differently. So for a purely elastic material, Hooke's law says that you can model it with a spring. And the spring constant, which we learned before, is K, as describes how much energy the spring can hold. For an elastic material, that's actually the modulus. So the elastic modulus E is the proportionality constant between stress and strain, and it's linear. So strain over time is constant if you hold it at a constant stress. For purely viscous materials, a really common way to represent it is through a dashpot or a piston cylinder model, and then the stress is held constant here, and the strain rate is constant, but the strain itself changes over time. And so if you look at so basically you have stress here is directly related to the strain rate, the rate of change of strain by the proportionality constant of viscosity. So it's similar to Hooke's law, but it's related to the derivative of strain, not to actual strain. Okay, so this is a purely viscous material. There's a model for a viscoelastic material. A common one is the Maxwell model, where you have a spring and a dashpot aligned in series. And because it's in series, and the stress is constant, to get the strain rate, you can just add up the strain rates for the different components. The first one being for the dashpot, and then for the spring, you just plug it in for your known values that we talked about on the previous pages, and that's how you can describe the material in a viscous situation, in a viscoelastic situation. So this actually works pretty well for stress relaxation, but it's not adequate to describe creep. It's actually not adequate to describe stress relaxation either. It's just a simple model of viscoelasticity to show you that it's somewhere in between elastic and viscous. There's also the Voigt model, which is a spring and a dashpot in parallel, and so you can just add up the stress, and this works pretty well for creep, but not so well for stress relaxation. And actually, it doesn't work that well for either of them anyway. So, but these are different ways that they work well to describe different aspects of different tests. So there's more complicated models that still don't work, and this is an active area of generally mechanical engineering research where you're trying to come up with the perfect model for a viscoelastic material. You can hook them all up, all the springs and dash pots in series and parallel, and they can all account for a different material property of the viscoelastic material. But I'm not interested in that because I don't see how useful that can be when it doesn't actually work anyway. So you might as well just test the material and see what it actually does in real life. Okay, so those are our mechanical properties. Now we're going to keep going straight through into thermal properties. But since everything is related to those three things we talked about, chain entanglement, summation of forces, and the time scale, this should be just as logical as the rest of it. So just some definitions to start with. Polymers can be in either thermoplastic or thermosetting. Thermosets are cross-linked, and so they don't melt. So their thermal properties are less interesting than thermoplastics. So we're going to talk about thermoplastics. So this is a thermogram, or well, it's the mechanical properties versus temperature for amorphous polymers. And so it's really interesting because at low temperatures, it's all frozen and cold. Well, it's not actually, it's technically not frozen because it's amorphous, so it's not crystallized. But it's below this, what's called the glass transition temperature. And so below the glass transition temperature, it's in its glassy state. It's really brittle. The chains cannot freely rotate because there's not enough energy in the system because it's so cold. As soon as you get to that temperature that is above, that's called the glass transition temperature, that is the point at which you have enough energy available for the bonds to be able to rotate again. That's where you see more movement. So that's why below the TG, you have a glassy state. The materials can be really brittle and they'll behave like a glass. And above that, they behave more like what you think of as a polymer. And then you keep increasing the temperature, and eventually they'll melt and flow as liquids. So that is for an amorphous polymer. For semicrystalline polymers, so we have, on this graph, we have amorphous, it's the same plot along the bottom there, but then for semicrystalline, the amorphous regions that they have also follow the same rules as the amorphous polymers we just saw. So they have a glass transition region, but it's not so obvious to tell if you plot it because it's just, and maybe it would be, if it's just a small amount of crystallinity in the polymer, you would see it more. But you don't see it as much on this plot. What else did I want to say about this? So the TG is really important. It's kind of weird to think about. A lot of times people confuse it with the melting temperature, but they're really different in a lot of ways. And they both exist for polymers at very different spots, very different temperatures. So the glass transition temperature is the amorphous region that it starts behaving. It starts having enough energy to move. If you're below the TG, it's a disordered solid with immobile molecules that maybe they'll vibrate a little bit because you're not at 0 Kelvin, but they're not going to move around like they do in a normal polymer. And then above the TG, they can move around. For the melting temperature, that's only the crystalline region we're talking about. And below the melting temperature, which is all, when you're working with a material, if it's not melted, if it's not liquid, then it's below its melting temperature. And that's going to be very ordered and crystalline, and then above that it becomes a disordered melt. So melting, if you recall, is just when the chains are all completely disordered. That's like the definition of melting. So what happens when you increase temperature on mechanical properties? We talked earlier about what happens when you increase strain rate. It makes the modulus go higher, and so you can see that it's going up like that. It's the same thing with temperature. Or with decreasing temperature as you get closer to that glassy region. And if you're in the glassy region, it's going to be brittle because now it behaves like a glass. So you can characterize thermal properties using differential scanning calorimetry, or DSC. And so this is an example scan. And this is really useful because all of these temperatures that these transitions happen are characteristic for a certain polymer. And that's how you can tell the difference between different polymers if you don't know what a sample is. I'm not sure why you would ever not know what a sample is, so that would not really be that useful. But what you might want to know is how crystalline is your sample. And so that is directly related to the size of the crystallization peak, which we see right here. So if you take the area of the crystallization peak, that's directly related to the degree of crystallinity of this semicrystalline polymer. Also, if you have any impurities in the polymer, which you probably will, that will depress the melting temperature, like we talked about before, because it hinders the crystallinity and the packing. So if that melting temperature, if you know that you made peak and it's supposed to be 339 degrees, if it's actually 300 degrees, there's some impurities there that depress the melting temperature. So this is actually a really useful method. Okay, so I think that when you're talking about thermal properties of polymers, I mean, with mechanical properties, it's easy to see why you need to know it because it's directly related to their performance. And with the thermal properties, you're not going to put a molten polymer into someone's body, so why do you need to know what these things are, right? So I wanted to introduce an aspect of polymer research that I think is really cool, and it's really new too, so it's actually not used clinically yet. But shape memory polymers are commonly based on their thermal transition temperatures. So shape memory polymer is one that has a permanent shape. So in this picture, it's the one on one on the bottom that's shaped like a tube. And as soon as if you change its if you somehow stimulate it with an external signal, it will lose that shape and maybe condense or something. And then when you release that external force, it'll return to the original shape that it started as. So a really common way to do that, as I said, is through thermal transition. So in this schematic, you have a permanent, so this is a schematic of the permanent shape that it's supposed to be in. And you have these network points, the black dots in the schematic, and this is its temperature that it's supposed to be, that it's permanently in. But then if you cool it to a transition temperature, T-trans, and you hold it at this, you temporarily stabilize it in that other shape, which in the picture are these weird coiled shapes. It'll stay there until you heat it up again back to its normal temperature, and then it springs back to the shape that you formed it in. So that's pretty cool, and you can make that transition temperature like the glass transition temperature, so that if you cool down to the glass transition temperature, it becomes like a very brittle, hard material that maybe you can even use as a needle and stick it into someone. Maybe it can go through someone, and then as soon as you get inside, it comes to 37 degrees, that's above its glass transition temperature, and returns to its bigger state. So some examples of using this in biomedical research are self-closing sutures, which the picture is not really great here, but it's pretty cool that if at room temperature the material is bigger, but then it condenses at body temperature, it tightens the suture and closes it without having to have any knots. So that's pretty cool. And then a self-opening stent is the opposite, where it's sort of what I was just talking about, where it's like condensed in a smaller form, and then you put it into an occluded artery, and then as soon as it gets to the correct temperature, it expands. And then you can also make it biodegradable as well, so that would naturally go away and never has to be removed. So this is a really cool and exciting area of polymer research that is just beginning now, and is a really useful application of the thermal transition properties. But you can also have other forces, like another really easy way to do it is having a magnetic force, so you can hold it in a magnetic conformation while the magnetic field is applied. It's held in a particular conformation, and you move the magnetic field and springs back to whatever shape it was supposed to be in. So that's pretty cool. Okay, so finally, whenever you're talking about a biomaterial, it's important to know how it interacts with the body. So I just wanted to point out here that a polymer deterioration starts even before you implant it into a body. You can have this random chain scission where the polymer literally just falls apart. That doesn't happen as much, but sterilization is a big problem with polymers. You can't use dry heat sterilization because it'll probably melt the polymer unless the polymer melting temperature is so high, or it's like a thermoset that it doesn't melt, so then you can use that. But for a lot of our purposes, it can't really be used. Steam sterilization is a no-no because a lot of polymers are sensitive to hydrolytic degradation by water vapor, so you don't want to use that. So you basically have to use like ethylene oxide gas, but that also can cause damage. You can also have radiation, but that causes damage too. Maybe it's just to the surface, but it causes damage. So these are all things you have to consider when you're designing a material. And then once you implant the biomaterial, you're going to have chemical degradation. mostly by hydrolysis, because a lot of polymers are just sensitive to attack by water, but also because you have a lot of ions and a lot of enzymes in the body that are going to attack it, just like we talked about with metals and ceramics last week. Mechanochemical effects, so of course you'll have mechanical wear in any place that you implant it, especially really high loading areas like the joint, and then that'll be compounded if you have any chemical processes that are also in the area. Polymers absorb small molecules, which then acts as plasticizers and completely start changing their properties because it affects the crystallinity and the packing, like we talked before. And they could just absorb water, making them swell, and then that changes their properties as well. So these are just all things that need to be tested and considered when you're designing a polymer. Okay, so polymers will degrade in vivo, so you might as well use that to your advantage and design a biodegradable polymer, which has been used extensively to design sutures. And so now when you go, if you have a simple cut and you need to get stitches, normally you do not have to go and have the stitches removed like you used to. They just degrade over time and you're fine. Biodegradable polymers are also really useful in drug delivery, so you can make polymeric microparticles that are hydrophobic, and you maybe encapsulate a hydrophilic protein or other drug, and then the release of the protein from the microparticles only happens by degradation of the polymer because it can't diffuse through the hydrophobic polymer. So as the material starts to degrade, the protein diffuses out, and you can completely control the release of that protein based on the polymer properties. But we're going to talk about biodegradation and also drug delivery a lot more in the second sequence of this course. So I'm not going to get into any more detail today. Biodegradable polymers are also hugely important for tissue engineering, and we're going to talk about that in the third term. So I'm not going to talk about that today either. But suffice it to say that biodegradable polymers are really useful. So in summary, the structure of polymers are extremely important for their properties, and it varies widely the properties vary widely depending on the structure. So you should be able to completely custom design a polymer for its intended use, which is nice. It's important to remember that their mechanical properties are time and temperature dependent. So you need to know at what temperature and they'll be responding to, and if you're modeling the stresses that are going to be going through a material, you have to understand that it's a viscoelastic response that you're looking at. Thank you.